Okay, so chapter 12, from 12 on to the end of the book, is all processing and processing related things, like how do you know if you've done a good job, right? What quality control and what sort of processing statistics can you apply to materials? So we'll start with synthesis. Synthesis is a good place to start with this stuff. And we've got all these different ceramics we've been talking about, we've been seeing pictures of, we know that they have certain applications. How do you get it from the raw materials to the material that you're then going to use? It's tricky, right? So let's start with what's involved in it, what are the raw materials, what are the steps involved in making it, right? So first off, you have to consider the materials where they're going to start from. We're going to cover powder processing, which takes into account shape and size, things like that. There's a pre-consolidation step, and then there's batching. That will all be covered in this chapter. So we won't even talk about like densifying it or shape forming or anything like that. That'll come in later chapters. Right now we're just going to do those things. So what are our traditional ceramic materials, right? When we say traditional ceramic materials, what are we talking about? Clay, right? The stuff that you did in like your elementary class when you made a mug or something, if you did that, right? Things like clay. What else? What are traditional? When you think of traditional, when you tell your parents you're taking a ceramic engineering class, what do they say? Like, pottery. I made a plate once, right? So glass, porcelain, cement. Maybe. Yeah, now you're talking. So porcelain, cement, glass. This is awkwardly low to write. What's that? Diamond. Yeah, they might say like they might have heard of things like gemstones, diamond, like opals, ruby. They've probably heard of words like these, and they may or may not realize that those are ceramics, right? But these are traditional, I'd say, materials, right? So these are important. They're enormously important. We'll be talking about them a little bit more as we go. But then there's a whole bunch of what I'd say are modern ceramics or technological ceramics. We'll get to those in a moment too. So let's begin with some of these traditional ones, right? If you take rocks, if I go outside and find the first rock I see, and I grind it up, is it a clay? Is it just the fact that you grind something up and get it small, and then you mix that with water, does it turn into a clay? No, what's the fundamental difference between clays? We've learned about these. What do all clays have that is like that fundamental building block?
Water into the mica crystal structure.
Yeah, it's kind of like a mica crystal structure, which involved what? You guys remember?
Water
you said water.
Layers.
Yeah, it's not exactly water between the layers. Water can get sucked in between the layers, but the only reason that works is because you've got these layers that are generally van der Waals bonded together, so weak binding between those layers. And then what's the main constituent these things have to have? It's clay. What type of silicate group does it have? No, it's a silicon oxygen tetrahedra, but how are those put together? Is it a 3D network? No, it's a 2D network of SiO4, right? So it's actually an Si2O5, right? If you remember, it forms these ring-like structures, right? Where these are all Si2O5, right? And that obviously doesn't charge balance, right? Because you've got positive 8 and negative 10. So this is overall minus 2. So you have to pick up some additional positive charge. And that's what the layers nearby are essentially doing. But this layered structure is present in clays, right? When this is present, that leads to OH groups getting added onto this, so it gets hydrated. So two things to take away. If it's got this Si2O5 two-dimensional layer, and it's hydrated with hydroxide groups, OH groups, it's a clay. Right? It's in the clay family anyways. So if you take a rock and grind it up and it doesn't have those hydroxide groups to start with, or if it doesn't have this two-dimensional structure, you're not going to have a clay just by grinding it up. You're going to have smaller bits of that same rock, right? Whatever that rock was to start with, limestone or calcium carbonate, whatever it was, right? So let's consider some of our clays. We said that there's kaolinite. So again, this is that same structure we talked about, right? Si2O5, that's the one. So there's two Si2O5s, there's some of these aluminum hydroxide groups, and it builds up a layered structure, right? How do these come to exist, right? How does this clay come to be? Here's where it comes with like the rock grinding, right? If you take rock and you grind it up, let's say you ground up something that has aluminum and silicon, but it's a rock, right? But then this sits at the bottom of a lake for a very, very long time, or a river. Now you've given it a constant source of water. The conversion from the minerals that aren't hydroxides to this hydroxide must have a negative free energy because it happens spontaneously. But in the presence of water, but typically slowly over very long time, it converts these things, which is why when you go to get clay, you go to river bottoms or like river deltas. like, this all used to be Lake Bonneville, right? And in Davis County, where I grew up, all of Davis County is on clay, basically. It was a giant delta. It's all clay up there, so they can actually dig it right out of the dirt. There's a lot of clay up there, right? So it has to do with the geology and how these things are formed, largely. Things that are kind of outside of our control. We can choose to put our minds in different places, but essentially these things, we don't manufacture them ourselves. We basically dig them out of the ground. We could make them, and heaven knows we can make things. We learn how to make stuff. It's just not going to be cost effective. It's going to be an expensive process. You want to start with something that's as cheap as possible for your final product, and so they dig it out of the ground, right? So yeah, rock weathers to form feldspar. Here's the feldspar family. It's got the cation and aluminum silicates, AlSi3O8. So the whole family of materials, these get left underwater and they convert down, they break down to clays in the presence of water. Right? What other materials are traditionally used? Things like asbestos. Asbestos was like, it's got, rightly so, a very bad reputation right nowadays. But in the 50s, not the case. Asbestos was like, people love this stuff. They made everything out of asbestos, right? You made floors. Actually, one room in my house still has tiles like this in the basement. And before you panic, like, not a big deal if it's in a tile, because it's not getting aerosolized. But when you rip that tile out, if we ever want to put carpet or hardwood or just not asbestos in there, that's the issue. That's when you have to have the ventilation protection. Why? Do you know why? Yeah, Barrett?
It's tiny little crystal fibers that float in the air.
These things. Right? Asbestos as a mineral, as they make it, and so present in this, if you zoomed in on a microscope, you can see a bunch of small regions like this, where we call this the habit, the crystal habit. Habit describes sort of the morphology of the grains. Are they plate-like? So you hear people describe a platey habit. That means that they grow in plates. Kind of ice crystals sometimes grow in platey habits. And then other times, depending on temperature, humidity, ice will grow in rods, and it'll be rod-like habit. And this grows in a fibrous habit. They would have this, right? So how these things grow depends on a lot of conditions, right? So for right now, we'll just say that some materials can have multiple different habits, and asbestos is one that has a negative habit because these tiny fibers are so small they can get airborne, they get in your lungs, and it causes cystic fibrosis and other problems. So it was a great material because it was cheap and it was nice to work with. It was a friendly ceramic in terms of processing, but it's a really crappy one in terms of impact on health, right? And interesting story, I was looking at this. Asbestos, I was wondering where it came from. It comes from Canada. And if you pull up this map, it comes from there's a town called Asbestos, Canada, right? Here's your town, right here. It gets better if you look at the Google image. The Earth image. Right? Oh, wow. The giant mine where all of our asbestos is coming from, tiny little town. Something like that next to it. Anyways. So a huge mine, not unlike the strip mine that we have for copper here. But like I said, asbestos used to be a booming industry because it was used for everything. It was such a nice ceramic to work with. Once you realize it was not so great, asbestos has really fallen off. I'm sure it still has applications. I just don't think it's used very widely because the stigma with it now. It's actually chemically pretty similar to talc. If anybody are rock climbers, your chalk bag is probably talc. The other stuff, the talc's a common one that they use. Talc is, so the formula for asbestos was what? It was Mg3, Si2O5, and some hydroxide groups. Whereas talc is what? Mg3, and now you've got SiO3. So what does that tell you? When they write things in parentheses like this, it's trying to help you understand the structure by writing the formula in a certain way, right? The other one had Si2O5 groups, which is what, these layered things. This is SiO3, which I'm guessing is a different bonding motif. You probably don't have these layered things anymore. I don't know that for sure. I have to pull up the structure, right? In any case, talc, it's interesting because of a couple things. First off, it's the softest mineral. If you look at the Mohs hardness scale, this is basically measuring different gems or naturally occurring materials and their relative hardness one to another. So the very lowest numbers would be our softest materials, and that's talc. Obviously, the hardest would be diamond. And these differences are not uniform. Like the difference from here to here is 300% harder, whereas these could be 10%. So they're not uniform, but this is a general scale. And back in the day, before we had nice measurements of hardness, this is kind of what they did. People who were geologists had a box with these 9 minerals. They didn't have diamond in there. But they had these 9 minerals in a little box, and they'd go out geologing, whatever they do. And they'd take the mineral and they'd try and scratch something, and they'd say, what is this material? Well, we don't have X-ray diffraction, we don't have it in the field with us, but I can scratch it with that and not with this, and it's this color, and we found it in this location, so it's probably such and such a mineral. That's kind of how they did it. Kind of interesting. All right, so that's some of the traditional ceramics. We could go on. There's a lot more traditional ceramics, but for this class, let's focus on the technological modern ceramics. Like what? Good examples. What are our technological modern ceramics? What have you guys been doing your spotlights on? Yeah, Barrett?
There's aluminum.
Aluminum. That one kind of straddles the line. Aluminum's been around for a long, long time. It's been used as a traditional ceramic, but it has applications all over the place as a technical ceramic because we've gotten better at working with it and we've modified this microstructure a little bit. So that one sort of is in both camps. What other modern technical ceramics do you use? Talking about it for a couple months. YAG. What else? Silicon nitride. Silicon carbide, right? We got a big long list of these things, right? Zirconia, thorium oxide as a fuel, beryllium oxide, magnetic ceramics, all the YAG, ferrite, nuclear fuel, UO2, right? All sorts of things. We can go on and on. Cutting materials like borides and carbides. Go on and on and on, right? So what's the principal difference between our traditional ceramics and these technological ceramics? Is there a difference?
Just a process.
Yeah, basically they could be the same, but generally speaking, a lot of these things you can't just dig it right out of the ground and have it ready to go. You're not going to find like this nice thing maybe ready to go out of the ground. You probably have to make it, right? And then if you do dig it out of the ground, the control over morphology, phases present, dopants, most of that's out the window. You can't dig like a gemstone out of the ground and it's going to have maybe something really nice going on, but most of the time it's a mixed bag. You're going to have lots of different things. And for technological ceramics, you want to control, maybe even really precisely control dopants, right? You want 8YZ, meaning 8 mole percent yttrium and zirconia as opposed to 3YZ, where it's 3 mole percent, right? You want to be able to control that. And so I'd say the main difference here is control over purity. And purity is both in terms of phases present and composition. This is such an awkward height. You've got a chair. Okay. And then you've also got things like ruby, which is just alumina, or they've got sapphire, right? And you can dig these things, gemstones, out of the ground, but a lot of times, what if you want like a ruby that's in the shape of a rod, right? Like a long rod, or a sapphire rod, right? Right now you can buy these things. Are they actually finding a giant gemstone of sapphire ruby and coring it, drilling a rod? No way. That's crazy. These giant things are worth lots and lots of money. There's actually just a really interesting article in Wired about the world's largest emerald that's ever been found and the bloody, bloody, bloody wake of destruction that's left behind it, because it's like as big as, I can hear it's humongous. And so it's really worthwhile. If you had something big, you certainly wouldn't take that and cut and make a little rod and sell to a scientist. We couldn't afford it, right? So instead, we have to find a way to make these things. So what's the difference between Al2O3 that's in your spark plug and the ruby that's in like a laser, for example, laser pattern? What's the difference? Right? Well, dopants for one thing. Yeah, ruby, we call it ruby because we doped aluminum with a little bit of chromium in it, alumina, right? What else is different? Principal difference is not only composition, but
Other phases.
phases present, sure. This might have a little bit of magnesium and other stuff, right? So it's very, very pure, except for if you want to intentionally add chromium, and then it's single crystal. Normally we talk about these things being single crystal, right? If you like a laser cavity, or lots and lots of applications you want to grow single crystals. Like we just published, actually, Mike and I, on growing some single crystals.
Cadmium arsenide?
Cadmium telluride. We did grow cadmium arsenide though, right? Journal, crystal growth, sparks, Scarpula. Let me show you what we just grew. What's that?
You have the carrot?
Yeah. So we just grew this one. I'll show you what we just grew. This actually just got published last week. Why do you want single crystals again? Can you think of an instance? Highly ordered. What do we mean by that? What do we mean by highly ordered? Yeah, so maybe like if grain boundaries are a slipping point, oftentimes grain boundaries strengthen things because dislocations get deflected, but they can also be sliding points for creep and stuff, so they can provide some strength. What else do we use them for?
Electronics.
Where are the figures? So this is still just barely hot off the press, so they haven't actually organized it nicely. So you should be able to see. Okay, here's our crystal, right? So we grew a single crystal. we started out by melting a bunch of the different elements together. You have the feed, which is polycrystalline. What's the feed? It means something that's going to eventually turn into a single crystal. It's the feedstock. You've got the cadmium solution, so you've got a liquid phase, right? So the feedstock you're going to melt into this phase. And then as this slowly cools, you're going to form a single crystal, which is going to grow that way. How do you do this? How do you achieve this? So Josh already knows. Eric, I'm guessing already knows. Anybody want to take a guess that might know? How would you do this? Like, we clearly have, like, this was not melted. We melted this section, and then this solidified. How would you do this? We're going to talk about this later on in the next chapter, I think. So maybe brainstorm with a friend real quick. How might you go about this, right? What's that?
Ryan's pretty close.
Okay. Let's hear it, Ryan. How might you do it?
So, with how it is, like if you had just like a heated ring or something, and you were just passing it through.
That's exactly right. I mean, the actual furnace is more than just like a heated ring, but that's basically the idea. Rather than putting this whole thing in a furnace where it's all going to melt, right? And then as you cool it down, it's going to start to crystallize from all over the place, and you'll have just like any alloy that you, I guess we call them ingots when you melt it, and now it's got the solidified shape. Rather than that, you want to control very carefully where it grows from so that you only get one nucleation site. So you put this thing in a sort of a quartz ampule. Actually, I better double check that. I'm pretty sure it is. Right? I think it was actually sitting vertically when we did the test. The furnace is called a moving furnace, where you can move the heating zone. So you can either move the furnace. There's sort of two ways to do this. You can You can either move your sample, or you can move the heating profile in your furnace, right? So here's our sample, right? So it's filled with stuff. You want to have a molten zone, and you want to have your crystal, right? So you can either have a bunch of different furnace elements that are going around this thing, right? And you could control, you could say, all right, at time t equals whatever, we want these to be hot, so hot that this is molten, we want these to be cold, and this to be cold, right? And you could change these furnace elements to do that. Those furnaces exist. They have like 30 or 40 different heating elements, and you just build a program that slowly changes how they change temperature. Or an easier way, and I'm pretty sure this is what we did on this crystal. I'd have to ask Akira. He actually did most of it. This whole thing moves though, right?
So the crystal is housed in a quartz ampule, and then it's just tied to a wire, and then it slowly lowers to the furnace.
Yeah, so you've got one hot zone. As you bring it down at first, it's all molten when it first hits that hot zone, and then as that starts to leave the hot zone, the thermodynamic driving force for it to solidify is starting to increase. If you do this really carefully, you can get just one spot to crystallize, one spot on here, and then as you slowly lower this thing out of the hot zone, it slowly grows a single crystal if you've done it right, and it takes a lot of work, right? So that's the idea behind single crystals. So doing that, you could grow all sorts of single crystals. You could grow them of, well, whatever is amenable to this process, and there's lots of other ways to do this, right? We'll talk about those next chapter. But I'd say, again, going back to the big differences between traditional and modern ceramics, has mostly to do with purity of phase, purity of composition. Although there's some shape forming techniques that also define modern ceramics. Yeah, Barrett?
So when you do that method, you have to make sure that like the insides of your cords are really, really smooth, so they
you betcha.
Going on the right direction.
Yeah, he etches it with hydrochloric acid before to clean it and to smooth it out.
This guy's great, by the way. We are very fortunate to have Akira here. He's from Japan, from a lab that does tons and tons of crystal growth. So we're stealing as much of his info as we can. We're having him teach us everything possible while he's here. And we've grown some big single crystals. And you saw how big that one was. My postdoc Q can grow them as big as your thumb. We've done for materials. The cadmium arsenide is a little bit smaller, but great stuff. All right, so let's start with some of the traditional materials. Actually, Chris did a great job of talking about this, the Bayer process. Bayer process is how we get alumina. Alumina is everywhere. Alumina is all over the place as a modern ceramic. But it comes from bauxite, and bauxite is not alumina. Bauxite is mostly aluminum hydroxide, and then critically it's mixed with iron impurities, hydroxides, silicates, and other impurities, right? So let's walk our way through this, and he did a great job of this. first off, we decided we'd wash it in hot NaOH. Why did we do that? And actually, they'll do it under pressure, right? So this is like a pressure cooker of a really caustic solution, right? Pretty nasty situation. You do that because you go from Al2O3, you add this sodium hydroxide, and you turn it into NaAlO2, which is what? A liquid. It's going to be a liquid at these temperatures, right? So that's great. You've dissolved it. So all of your alumina that you eventually want to get out is now in a liquid form. But some things don't dissolve, like iron impurities. Iron impurities would dissolve under acidic conditions as opposed to basic conditions. So by moving it towards basic, you basically have these things not solidified, or sorry, not liquefied. So they say solids, they're going to settle out and you can like separate them, right? Just because of mass to liquid separation. So that's nice. Problem though is that your silica, SiO2, does dissolve under basic conditions. It doesn't dissolve under acid very easily, unless you're using like HF, right? So your silica is still there, so you've got to get rid of that. How do they do it? They add lime. What's lime? What's lime again? Yeah, it's calcium oxide, or calcium carbonate would be like limestone, like calcium carbonate. But they add lime, CaO, because it forms CaSiO3, which is a solid now, right? So that reacts with all your silica, so you add as much lime until it's reacting with that. That's removed, now your solid impurities, they call this red mud, the calcium and the irons and the precipitates that come out of this. Red mud, there's a ton of it, I think you talked about this. It's all over the place. If you can find something nice to do with red mud, it would be a technological advancement. I'm sure they do something with them. But realize that's a waste material, meaning that's an opportunity. Like if you guys came up with a clever use of that, that's an interesting opportunity. I'm sure people do this, right? So now you need to turn this NaAlO2 back into alumina. So you need to get rid of the sodium, right? And there's two ways they did this. I think Chris talked about this, that they bubble hydrogen or carbon dioxide gas through it, bubble CO2 through here, you form the aluminum hydroxide, and this we don't care about, right? Nowadays, they actually put in an AlOH3 seed crystal, exactly like I'm showing you here. You got this thing molten, you put the seed crystal in, you touch it at the surface, and you start drawing it out. Outside is going to be colder temperature than the liquid, and so it's going to slowly solidify, and you grow these big single crystals. So both ways, I think this is actually the correct way to do that. Okay? And now you've got AlOH3, which is not what you want. You want Al2O3, so you fire this, you calcine it. Calcining is a heat treat. That's a word we use to describe in ceramics. A heat treating step to get the right phase, not to get the right final product. Right? It's not going to be dense. It's not going to be a lot of other things. The grain size might not be right, but you're going to have the right phase. Okay? Any questions so far on this? Is the not bauxite, Bayer process. Bayer process is for bauxite. Any questions? Yeah. Gabe?
So the powder that we use in the 3010 class, is that already Al2?
Are you making the chess pieces like that one?
Yeah, yeah.
That's definitely alpha aluminum, meaning it's already an Al2O3.
So it's already been calcined.
It's already been calcined, right? So if you modify that, if you guys dope those things or whatever, I don't think you do. I think some of the chess
We
pieces,
do, yeah.
in years past, they turn them blue and stuff by putting dopants in them. That would be part of the calcining process, not the sintering process. Sintering is when you go from the loose particles to your dense final product, right? But this is just to get the right phase, okay? So getting the right phase is important, and there's a bazillion different processes. Hopefully, as you guys are doing some of your ceramic spotlights, you'll identify what are key processes, like the Bayer process. Chris did a great job of it. Do something similar to that. Silicon carbide has an interesting one. So as you're doing these, try and find the process whereby it's made from its original materials. Okay, what else affects our raw materials, and what do we care about in raw materials? Shape, size, reactivity, purity, right? Those are some of the main things when you're talking about synthesis. You care about what comes out of the bottom in terms of shape, size, reactivity, and purity. Purity affects what? Melting point. What do we know about most materials? When you go from pure to anything other than pure, right? You're adding something to it. What do we typically do to the melting point? It tends to go down. There's exceptions to this rule. Things tend to go down, right? Eutectics start at high and then they go down as you go towards the mixture of those two things. Generally speaking, dopants or impurities lower the melting point, and that can be used to your advantage. You can add that like they do in magnesia into alumina, right? When you put magnesium into alumina, it actually causes it to melt a thin layer at the grain boundaries, which causes densification. So it's called a sintering or a densification aid, right? So if you add these intentionally, you can have these added for electronic, optical, magnetic properties. Heaven knows we've talked a lot about that this semester, right? You can do it to modify strength. How can strength be changed by impurities? Yeah, just like an alloy. When you start out with pure silver and you add a little bit of gold or copper to it, you're making, is sterling silver with gold in it? Is it copper? They add something to it, it's one of the two. But you start out and you think, hey, sterling silver, that's less silver, which is more expensive than copper, so it shouldn't be as good, right? But it's actually, even though you're adding something that's less costly, you're getting a better final product because that copper does what? It strengthens it. And how come? How does it do it? Yeah, solid solution strengthening, which is, I don't know. You guys are taking 2010. I believe in you. Turn to your neighbor. Tell him how it works. Okay, how does solid solution strengthening work? Anybody want to take a stab at it? Ashley, I believe in you.
The interstitials kind of lock everything into place.
Yeah, if they're interstitials, then things can't move because there's the strain field, right? It doesn't even have to be interstitial, right? What if in the place of this chair right here, right, I put like a grand piano, right? How easy is it going to be for me to like slide these rows of chairs past one another? It's not gonna be very easy because that grand piano messes things up, right? So even if it's not interstitial, if it's just bigger or smaller than the normal site is, it's gonna have a strain field associated with it that messes up dislocation motion. If dislocations can't move, you made it stronger but less ductile, right? Fair?
So we were talking about this a little bit. Where's the transition between it becoming so brittle that it's not strong?
Well, it will get stronger and stronger, but its toughness will go down for sure, right? So there's a trait like ceramics, for example. Ceramics are very strong. The point at which they break is actually quite high for many of these things, but we don't call them tough. You don't use them in instances where toughness is required because they're so brittle. Right? All right, so it can affect creep, coefficient of expansion, modulus. It can affect all these things, right? Purity affects, as we've been talking about for the first half of the semester, a lot of the properties we know and care about. Some properties depend on what the doping is there, right? So aliovalent doping creates defects. An example is yttrious stabilized zirconia. You put the yttrium on the zirconium site, it's 3+ instead of 4+, that creates oxygen vacancies. Oxygen vacancies are why we use that material for the most part, right? It means it's an oxygen ion conductor, right? So sometimes you add these things specifically in an aliovalent fashion. What's aliovalent mean? Not the same valence, right? It's not 4+ going on a 4+ side, it's 3+ going on a 4+, or 2+ or 5+, right? Isovalent means it's the same valence, right? Isovalence may not create those defects, right? You can have, so particle size, what do we care about particle size? Particle size affects your packing density, right? Packing density turns out to be like the bane of our existence with ceramics. It is the root of most of the problems we have is density. Density is related to packing density, right? So what do I mean by that? Well, if you have one particle size distribution, meaning you could somehow make sure every single particle of your ceramic, on even as small as it is all the same size, right? If you put those together, then it's just like packing of same size atoms, right? And what's the densest we can get? What's the densest crystal structure for our metal crystal structure? HCP or FCC. And how dense is it if you do the atomic packing fraction? Close to 80, it's 74%, meaning mono size, meaning the same size particles, you're never going to get better than 74%. So you're always going to have somewhere around here left in pores, right? What if you use two different atoms and you got a small atom, right? Or in this case, you've got a big particle and a small particle. You could put the small particles at the interstitial sites between the big particles, right? And you could fill up some of those voids. So now you're always going to have you're still going to have more than 26% porosity. So it's gone down a little bit. If you do 3 distributions, maybe down to 23. So you're starting to fill in the space, but it's a losing battle, right? Even if you go to like many distributions, it's approaching an asymptote. What is the asymptote? Does it approach? I don't know. This is an interesting math problem. We're not going to do it, right? But it's getting better, but it's not going to get you to 100%, right? Practically speaking, anyway.
Not with spheres.
Not with spheres, right? So what do? We have to get rid of those pores in another way. That's sintering. We'll talk about that in 2 chapters, I think. Yeah, Barrett?
You also feel okay.
Yeah, another phase. What if you did these particles in a liquid, right? Polymer or a liquid ceramic, something that's melted. That would clearly fill in some of these holes. So when we get to densification, those things become really important. The particle shape also affects packing. What if you have nice spheres, they're going to pack nicely. But what if you have like a big, long, rod-shaped thing? It's going to mess up your packing. So ideally, you want spheres to pack better. If you have irregular shapes, they don't pack as well. They don't pack as well, it leads to lots of problems, which we'll be getting to soon, right? Your initial packing density, your initial porosity, dictates your final porosity, right? If you only get it 60% dense to start with, it might dictate how far you're going to get it dense in your final product when you try and not melt the sinter it, right? So for example, this is for, I think it's for alumina. Yeah, in alumina. These lines show what your initial porosity was, 70, 65, 60, all the way down to 40, right? So if your thing was not very dense to start with, your initial porosity was 40%, so you got it 60% dense to start with, in what's called the green state. Green just means unfired, so like as you can pack it in the lab state. If you get it to 40 after a heat treatment, then your final porosity, here's your percent porosity when you're done, it's down to like 0.25%, right? So it's down to 0.25% porosity. That's great. It means you got rid of almost all your porosity in the firing. And your grain size was super small. Small grain size can be good, just depends on the application, whether you want the smaller or large, right? Whereas you took that same material, but you don't pack it very well to start with, and you got it 30% dense when you're making it, meaning there's 70% porosity. If you do the same heat treatment, you are left with, more than 10% porosity left over, and your grain size is going to be huge, right? So this basically dictates why it's so nice to get it as dense as possible, to get your initial porosity as low as possible before you do your sintering, because it influences your final process.
Are those initial processes in percent? The 70%?
Yeah. So what does 70% porous look like? It means like you just barely put this thing together, right? You put it in your press and you tapped it, right?
So,
that'll be around 70%
So the way you
porosity.
read this graph is like if it's 70% porous initially, and then you have
After a certain heat treatment, where I think all these are meant to have the same heat treatment,
okay.
or maybe they're saying it's after the best heat treatment possible. Even after they try and nuke this thing in a furnace and get it to sinter, this is as best as you're gonna get. I don't know how they prepared this data. It's in the book though. He might actually say a few more words about it. But the principle stands. If you don't get it very dense to start with, you're not gonna end up with a very nice product. And that sometimes what you're going for. When do we want porosity in a ceramic? High-tech ceramics all the time have porosity. When do we want it? So Barrett, answer all the time. Let me pick on somebody else who hasn't said something in a while. Let me pick on Mitch.
Large grain size?
Not large grain size. When do you want lots of porosity?
Oh, lots of porosity.
Is there an application for that?
Insulated material.
Yeah, bingo. Air is a really terrible conductor of heat. So if you got your ceramic, which is going to conduct better than air, generally speaking, you want to minimize the amount of ceramic, maximize the amount of air. You do that by having a bunch of little cavities, right? So like furnace linings that you guys use in labs, that's all intentionally designed to have large amounts of porosity, right? Anything else? Well, with large porosity comes large surface area. What can we do with large surface area? Yeah, in the back. Remind me your name. Ryan.
So would you want like devices where you're multiple
Yeah. Yeah, if you've got like your like when they do the artificial hip, if they were to put like fake bone or something in there and they want real bone to grow into the fake bone so it's like strong and actually gonna heal up, a little bit of porosity might actually be desirable. Because if it's just like a totally solid, dense ceramic, it's gonna stick maybe a little to the surface, but nothing as well as if it were to grow into it. Yeah, Ashley?
Like metal organic frameworks for drug delivery and furniture.
Huge. That's huge, yeah. Metal organic frameworks is an important topic. Chemists have taken over this. It's a ceramic, right? Zeolites, these are ceramics. Even though chemists mostly use them, we still love chemists, right? But those are important for a lot of things because they have giant cages. How does zeolites work again? I know we talked about it. They're giant cages of atoms that have big cavities in them. You can put molecules in there. You could have gas flow through those, so you can use them as filters or like drug delivery as sponges basically for something. Really, really important class of materials. All right, one last one, Bear. It's gone?
Oh wait, solid state electrolytes?
Electrolytes. Do you want a porous electrolyte? I don't know if they're used for that. I don't think so. I could be proven wrong. I don't know of one. Because generally you want ion conduction through there, and an air gap is not going to allow an ion to conduct through it. I could be wrong. There could be an instance where they do use them. I don't know of it. Okay, reactivity. More surface area on your particle, generally more reactive, right? If you're going to use this thing and your sintering process requires it to actually react to the second phase to get your final product, oftentimes these are called reaction bonded ceramics. Take component A, component B. When you heat it up, they don't just diffuse into one another. They're going to react to form a third product. You want to encourage reactivity by having higher surface areas. So maybe in your initial materials you want high surface area. So how do you get the right size of particles? One thing you can do is sieving, right? Where you take a screen or a sieve and you put your powder as received from Alcoa, right? They provide alumina, Alcoa alumina. You scoop it out by the cup or whatever, you plop it in this thing, and some of it, if it's small enough, is going to pass through these little mesh openings, right? So then you'd say you could define that as being a certain size where you know the particles are all at least no larger than a certain size, because you know that these holes in the screen are a certain size. So it says that you've got a big range, but it's at least no bigger than something else. That's a good start. That throws out any really big particles, which are called agglomerates in ceramics and cause hell on earth. They're terrible, right? So we can get rid of those, but you really like one distribution. So how do you get one distribution using sieves? Use a bunch of sieves, right? That's exactly what they do. They stack these things up like this. This is like usually on like a paint shaker, so it's like rotating, or it's like shaking. It's doing something such that if you put a bunch of your powder up top here, it like vibrates its way down, and the really small stuff will make it to the bottom. Really big stuff gets caught here, and you've got ranges that get caught in these intermediate pans. And this happens right now. It's really easy to do. You can do pretty big batches like this. It's not like industrially scalable, but you can do. It's kind of industrial. It's not the best way for doing huge amounts of stuff, but it's an okay way to separate or classify particles. Sometimes they say classify, they're talking about like separating out into sizes. Fair?
When we're looking at something that's like a polishing fluid, so when we see like a 0.3 micron diameter aluminum particles,
Yeah.
is that saying that that's the largest size, or that they've done this and it's actually?
I don't know offhand. You'd have to contact Bueller and ask what that number means. I would assume it means it's the largest, but I don't know that for sure. It's a really good question. You'll hear talk about mesh numbers, like what's the mesh number of that sieve? All they're referring to, the mesh size tells you how many openings per square inch there are. So you could have a mesh that's 4, meaning 4 openings per square inch. That means that your openings are the size of, I don't know, like a grape or not a grape, a blueberry, right? Pretty big. Or you could have 2,500 openings per square inch, which means that your openings are tiny, 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 right? So that's what these sieve numbers mean. Unfortunately, they talk about sieve numbers more often than the size of the opening. To me, it would make more sense to talk about the size of the opening, but convention is to talk about the sieve number. So you'll hear say, this powder is 2040 mesh. What does that mean? It means it passes a 20 mesh, but it gets stopped at a 40 mesh. It's big enough to get through a 20 mesh. It's too big to get through a 40 mesh. So it's a 2040 powder, 2040 mesh powder, right? That's this terminology you'll hear people use here. And if you do enough of them, you could stack 20 of these tall, you could actually get a really nice characterization of your powder particle size, right? You could say, so this is the cumulative percent fraction passing, right? So how much passes through a sieve with, all of it, 100% will pass through your largest openings, right? Sieve size opening around 1,000 microns, so a millimeter. So basically, everything passes through a millimeter. Nothing's larger than a millimeter in that, right? But then as they make this smaller and smaller, a smaller and smaller cumulative fraction of your stuff passes through it, until at this point, you have nothing smaller than 10 microns. So you know that all your powder lies somewhere between basically 10 microns and a millimeter, right? And then if you have a bunch of these things in between, you can actually take the weight fraction that's caught in each one of these, and you could turn those into a histogram, like bucket these things, and come to find out, maybe the distributor told you that, hey, this is one distribution, and it's got such and such an average standard deviation. When you measure, you say, hey, this is actually a bimodal distribution. We've got 2 sizes of particles. It's not usually something to be upset about. It's usually a good thing, right? Well, it depends. It can be a good thing, right? But this is how you might do that. Are there other ways to measure size of particles? On sieves, clearly this works. You can't do it. Are there better or other ways to do it? You can throw it in SEM, and people do this. They'll try and code it, because oftentimes your particles may not be conducting. You have to solve the conduction problem. You're going to throw it in there, and you can look at them. But the problem there is that oftentimes, especially in the dry state, particles clump together. It's really hard to know if you're looking at one particle or an agglomeration. And that agglomeration is what's called a soft or a hard agglomerate. We'll talk about the difference later. Okay? What other ways to do this? You measure size, if not in SEM. What do you do, Josh?
So I've used a particle size analyzer.
Yeah.
You suspend it in solution, you shoot a laser at it, and it analyzes the scattering
Yep.
of the laser and tells you the particle size.
That's the best way to do it. You suspend it in liquid. Hopefully you can ultrasonicate it in that liquid so it breaks up any soft agglomerates, right? So now the particles should be separate. You can add things to make them actually repel from one another. We'll talk about that later. Dispersants is what they're called. And then you shine light through there, and light will diffract. It'll basically, it'll change its direction depending on the size of the particles, right? So you can get a really good, you can get a very nice curve of the distribution of particles in it, and it's a lot easier to do than this. This would take all those different sieves. It'd probably be big and messy and loud. It'd take a long time. Particle size analyzer is, I don't know, 5 minutes.
Yeah.
It's very fast, whatever it is. I haven't used it recently. Yeah, Barry, do you have a comment?
I have a question. Is that kind of like when in astronomy you're looking at a star and you see like a tiny pass in front of it? It changes the brightness of that. So we're looking for a high brightness of
I don't
laser.
know. That's a good question. I do not know the answer to that.
One thing you have to put into the program is the refractive index of the material. So it's dealing with like just the light diffracting, and like we're talking about 3011 light diffracting.
What if you don't know it? If it's an unknown, is there just like a standard value you can use as an estimate?
You can put stuff in there, see how it changes. It's hard.
I don't know that.
But you can calculate, because you have to have the real and imaginary part of the refractive index. You can calculate the imaginary part from the absorption coefficient.
Interesting. So we submitted a grant for one of these a couple years ago and didn't get it. We'll be getting one at some point. We'll try it again one of these years. So let me ask you this. If you're doing this whole sieving process, is it better or worse wet? What if you take your powders and get them wet? Is it better or worse? Worse. We got to vote for worse. You have to dry them. That's really the downside of white. If it is worse, it's going to be because you have to dry it afterwards.
So is it wet or is it like in solution?
In solution. So like you make like a runny mud.
Is it better?
Some people think better. It certainly might help break up the particles a little bit better. You can ultrasonicate in the liquid state and break up the agglomerates. That might be
Did
useful.
it wet, and it was terrible.
What's that?
I did it wet, and it was terrible.
It makes a huge mess, I'll tell you that. It's harder to clean. But generally speaking, you do get better passage through the sieves. You have the potential to separate it better, but it is totally dependent on whether or not you can dry it, and when you dry it, if the particles don't agglomerate. If they clump together, all of a sudden you've got a really big particle when you expected it to be a nice certain size. So wet sieving can be better. In principle, it can be better because the liquid can help carry it through, so it can be faster, it can break up the agglomerates. But if you don't have a way of getting rid of that solution afterwards and getting back to your particles in their size where you think they're at, it's not going to be better. So they do use it, but it's tricky. What would be something you could do? Instead of using water, what might you use that might dry a little bit better? Ethanol is better, acetone's even better than that, hexane's even better than that, right? So you can use different solvents that will have less propensity to agglomerate or form agglomerates. But yeah, it can be used. It will make a mess. Okay, other ways to separate. There's something called the air classifier. This is what you want to do if you're doing like industrial scale, really huge amounts of stuff, because it's so fast. You could do so much separation. You could do anywhere from 400 tons an hour of dirt separated. So we're talking about like Kennecott has air classifiers, right? When they are digging their copper ore out of the ground before they go through the process of turning it into copper metal for us. I'm certain they use something like an air classifier. How does it work? It's pretty clever. It has pros and cons. Pros, that it's so fast, it can do huge amounts. Downside, you just get one classification. You get one binary split. Bigger or smaller than this number. That's really what you're stuck with. So you don't get a bunch of these little tiny bucketed values unless you had a whole bunch of these machines, and they're typically pretty big. So it works really well as a good initial separation. How does it work? So in comes your mixture of big and small particles, the red and green there. You've got your big and your small things, right? They fall down into this, and this thing is spinning, right? As it's spinning, what's going to happen? If I took a plate and I'm spinning like a pinwheel, right? This thing's spinning, and I pour dirt on it, what's going to happen to it? Fly outwards, right? Centrifugal force is going to act on it. It's going to get accelerated outwards, right? So if it gets accelerated outwards and it's a heavy particle, it will just get flung to the edges and go down. If it's a really small particle, you can imagine this. If you took like flour and you put it on like a merry-go-round that's going really fast, if I start pouring flour on there, it's just going to like go up in the air like crazy. This takes advantage of that. In fact, they blow a little bit of air in there. Oftentimes, they'll have like a counter current of air blowing this way, which carries these small particles up and around to another channel. So the red will go one place, the green will go another. It's taking advantage of the fact that you can force tiny particles to defy gravity a little bit when you blow air. If air is your elutriation media here. Elutriation is this process, right? So it can be done in air, or it can be done in liquid, right? You can have a liquid elutriation system, right? Now you've got a flowing media, right? So you've got some sort of liquid flowing through here, right? But this thing's spinning at the same time, right? So this whole thing would be spinning such that gravity, like the centrifugal force is pushing everything that way, right? But the flowing media, liquid or whatever you're using, is actually flowing that way. So again, heavy particles get pushed that way, small particles would get carried with the media out, right? So there's lots and lots of different elutriation type setups to separate things. And again, pros and cons. Pro, super fast. Con, you're getting one separation really, okay? How can we change particle size, right? So great, you ordered it from Alcoa, you tested its size, and they said it was going to be 10 microns. It's actually 100 microns. Like, dang it, we need 10 microns for this project. What do? You can reduce the particle size, right? You can change particles. You make it go up or down, right? To make it go down, the cheapest, easiest, most common way to do this is ball milling, right? You take a Nalgene bottle, you put your material in here that you want to break the particle size up, and you put a bunch of hard media inside of there, right? What do they use for media? Things like alumina, zirconia, steel, tungsten carbide. There's lots and lots of different ones that you can choose, and they basically use them, the cheapest one that'll get the job done. Tungsten carbide's great. It's really, really hard, and it has a high fracture toughness, meaning it won't chip and make impurities, but it's like bonkers expensive. It's terrible, right? Whereas steel is really, really cheap, but it's so soft and ductile, it may not melt things very quickly, and it's going to leave a bunch of steel left behind in your final product, right? So it's just trade-offs you have to make with this, right? How does it work? This thing rotates, they go up the wall, and they fall back down. It's as simple as that. This little media falls down, it pinches that stuff between the other media, it breaks it, right? Kind of surprised this actually works, but if you let it run for a day, a week, you can actually reduce your particle size pretty significantly. This is, it's easy, it's scalable, it's really slow. It's pretty terrible actually in terms of speed. So you can do better. You can do high energy ball milling, sometimes called a planetary mill. A planetary mill, this bowl itself is going to rotate that way, right, counterclockwise, but the whole bowl, even as it's rotating counterclockwise, is going to rotate clockwise on a much larger arc. So they call this a planetary mill. Like our Earth is rotating like one day at a time, right? It's spinning, 24 hours we're spinning, but we're also rotating around the sun. So that it's kind of a similar effect. And by doing so, you can generate just like huge G-forces. You can cause this thing to slam against that, right? Rather than just gravity causing it to cascade down and hit it, you're sort of slamming it. So you're really increasing the energy of each collision. Higher energy, better odds that you're going to break the stuff up, right? So we have one of these. This is harder to scale. You can do them in a couple hundred grams at a time. It gets tough to scale this up though, right? Again, lots of choices for your media, milling media. I think we had mentioned silicon nitride or silica, but those are also on the table. You really want to pick the one that will mill it the fastest while preventing unacceptable levels of contamination. Steel contaminates like crazy, but maybe because it's a steel, you can dissolve it in an acid afterwards, and your ceramic won't dissolve in an acid, right? Or you could remove it with like a magnet, right? So there's some ways where you accept that because this is cheap and nice to work with, and then you just know that it's going to contaminate it, and you're going to actively remove that contaminant afterwards. You're not going to remove tungsten carbide once it's in there. That's going to be really tough to separate. And you'll see this in papers where they actually use these different techniques. If they're careful and they do like a SEM image of their final product, you might see, even though they were making, for example, a group we knew, they were making magnesium silicide. So they were ball milling magnesium and silicon together to sort of mix these things together. In their final product, there's big chunks of tungsten carbide in there, right? Which could be really deleterious to your final product, right? Why? Why do you care? What potential downside if you got chunks of this leftover material? Is that really an issue? It's a flaw, right? So it's a flaw for one thing. What stress will it cause? What could be the origin of stress with an impurity like this? You want a nice alumina chess piece, right? But as you're doing it, you got some tungsten carbide in there. That's now part of your sintered chess piece pawn, right? So who cares? Does it matter? What can cause stress there? Yeah.
typically the ceramic will shrink while you're like sinking it, and maybe as you're shrinking it, that same piece doesn't shrink and separate.
Yes, these things, are they dense? Yeah, you betcha. These are already as dense as you can get them. They're milling media. You want them to be fully dense or as close as possible. So when you have now a bunch of loose particles around that that are filled with porosity, at least 30% porosity, if not more, the ceramic around it wants to shrink to fill in that porosity, something we'll talk about a lot in 2 more chapters. And that piece of milling media can't shrink, and so that creates stresses, creates really big stresses actually. So this would be known as a hard agglomerate, a piece of something that was not able to shrink as everything else around it shrinks. We call that a hard agglomerate in ceramics, and it causes things to break, basically, when you're sinking them. They've got big cracks, and like, why, what did this happen? You had a hard agglomerate, probably. Meaning you had a difference in density as it tried to shrink and it couldn't, right? We're out of time, so we'll pick up here next time and talk about some more synthesis.